Hello, everyone. Welcome back. Today, we're going to be talking a little bit about energy and chemical reactions. So now we've entered the part of the course that we're through stereochemistry and all of the 3D orientation stuff, and we're back to doing the interesting and fun part of chemistry, which is all about chemical reactions. And the first thing that we really need to cover is the idea of energy and relation to chemical reactions. And we've talked about this a little bit back when we were talking about acid-base chemistry, but now we're going to get a little deeper into it because we're going to need to start understanding everything about energy. So you may remember previously we drew some energy diagrams that look a little bit like this, right? Where they have energy on the y-axis and they have reaction progress on the x-axis. And these usually follow a very similar path where they start out at some energy for the reactants, they end at some energy for the products. It goes up and down a little hill, and that is the energy diagram there. And what we identified before was that if you trace a dotted line out from the reactants, it'll be either above or below the products, and the difference in energies here is the delta H. Okay? And that delta H is, of course, enthalpy, which you learned back in Gen Chem. But it does come back here now. And remember that enthalpy is just talking about things like bonds breaking and bonds forming. Okay? But there are a couple other things on this energy diagram that actually matter to us, right? For example, from that dotted line that we drew to the reactants, the difference between the top of the peak and that line is EA, also known as activation energy. All right. And activation energy is very important because it essentially relates to something we call kinetics. All right. The last little thing is right here at the top of the peak. We can label it with this double dagger, right, where it's kind of like two crosses. And this is what we call our transition state. Transition state. And so all of these come together to kind of make our energy diagram. And of course, each one is very important. Now, with that being said, there's two different terms that you're going to hear us talk about, which are relatively important. And the first one is thermodynamics. All right. And thermodynamics is essentially just talking about the total energy values in the system. All right. So it's related to enthalpy. So whether or not your enthalpy is positive or negative, that's all talking about what is called thermodynamics. On the other hand, we have something that is called kinetics, right? And back in Gen Chem, you've talked about both of these quite a bit, but kinetics for organic chemistry still work the exact same. We'll just talk about them slightly differently. And so this is essentially related to your activation energy, right? Or AKA the height of the peak. Okay. And so when we're talking about these two things, kinetics is thinking about the speed of the reaction, thermodynamics is thinking about the overall energy. All right. The last little bit is the transition state that we were talking about, right? And we'll just define this in a very loose term. We'll take a look at it in just a minute. But the transition state is essentially just showing what the molecule looks like while reacting, or the molecules, I guess. All right. So those are all the important things that we're going to see in these energy diagrams at the moment. So an energy diagram can give you a lot of information, right? But essentially, to get that information, you kind of have to know everything about them. And the first thing that I want to talk about with energy diagrams, an important thing which has to do with equilibrium that we didn't talk about beforehand, is the idea of something called microscopic reversibility. All right, and the idea of microscopic reversibility is that all reactions are reversible, and the reverse reaction is exactly opposite. of the forward reaction. And we saw this quite a bit in acid-base chemistry, but I wanted to put it into terms of a set of energy diagrams. All right, so let's say we had a forward and a reverse reaction. And we were looking at energy diagrams for them. Well, what we would see is that for the forward reaction, let's just say that we had something where our reactants were here, our products were here, and we're going up the hill. Okay? We would see that if we were to draw a dotted line from where the reactants are, our delta H in this case is going to be positive, right? Because it is going up to products. And remember that delta H is always products minus reactants. So that would be positive. And then our activation energy is sitting right here. It's quite large, right? So essentially, the principle of microscopic reversibility would say that if we were to then do the reverse reaction would be the exact same as the forward. But what you'll find interesting is if that is the case, then what we see is that now our reactant starts out higher than our product, right? Because essentially the product in the first one is technically our reactant here, because you can think about it as a reverse reaction. And then as we go down this reverse reaction path, we see that we draw a dotted line from the reactants to the products. Our delta H is now negative, and our activation energy is a lot smaller. And if you look at these energy diagrams in comparison to one another, what you would see is that these are mirror images of one another, right? Because the forward and the reverse are exact opposites, and they start out on different sides of the reaction, practically speaking. And so what this means is if we take a look at this in terms of thermodynamics and kinetics, we see something a little interesting, right? Because thermodynamically, the value of delta H is equal but opposite signs. So thermodynamically, one of these will be favorable, the other one will not, right? And the delta H that's negative is technically more favorable. So you would say that the reverse reaction is favorable. But then if we're talking about this kinetically, notice that also the reverse reaction has a much lower activation energy, right? And so since the forward reaction's activation energy is so much higher and the reverse is so much lower, the reverse reaction is going to be faster, right? So our activation energy changes and the reverse reaction is much faster. So with microscopic reversibility, um, the reactions will follow the exact same reaction path. However, the thermodynamics, all they do is change signs. The kinetics can actually change the activation energy quite a bit, right? They won't be the exact same, but opposite. They'll just change their value entirely. So, what does this actually mean with a real reaction, right? So let's do a real reaction example. And this is a reaction that we'll learn soon. You do not need to know this reaction right now. It will be talked about next week. Essentially, it's a reaction where we start out with this alkyl bromide, mix it with some water and some heat, and what we end up forming is all of these products here. All right. And keep in mind that the reason we bring up this microscopic reversibility idea is because everything's in equilibrium, right? And since everything is in equilibrium, this always applies because they can always, all reactions can go both ways. Okay? So let's take a look at this reaction in terms of the forward reaction steps. Okay? So for this reaction in the forward direction, essentially I'm going to draw what is called a reaction mechanism so that we can see each step and then we can kind of talk about the thermodynamics and kinetics of each. So starting from the alkyl bromide, for this specific reaction, what's going to happen is the bond between the carbon and the bromine is going to break, and the bromine is going to take the electrons because it's more electronegative. That is going to give us a carbon with a missing octet. We're also going to have some Br minus hanging out around there. But at this point, the water comes in as H2O, and it's going to do a Lewis acid-base chemistry. Oh, whoops, sorry, I didn't mean to do that. It's going to do a Bronsted, actually. I was thinking of a different reaction there for a second. And so it's going to deprotonate this proton here, and you're going to form an alkene between those two carbons. So what you end up with is you make the alkene, and you have that H3O plus, and then the Br minus that was just chilling out over there. Okay, so these are the two steps of the reaction. This first one was step one. The second one was step two. And so if we were to draw an energy diagram of this, right, what we would see is we're just gonna put the reactants right here, right? There's our reactants. And the first step is going to be pretty energetically unfavorable, right? Because we're going from a stable neutral molecule. We're generating charges, and more importantly, we're making a carbon that's lacking an octet. So that's going to come up here to our intermediates, right? So I just means intermediate. And then it's going to go downhill, right? Because now we're fulfilling that octet. And we'll talk about the energetics of this later on, but I'll tell you that the reactants are higher than the products. So this is our energy diagram here, right? And we do have these two transition states in between that we'll be talking about in just a minute. But if we think about this thermodynamically, right, we can draw that line that we've been drawing this whole time. Now there's a little bit more to think about, right? Because we have this difference between the reactant and the intermediate. That's a delta H. We have this difference between the reactant and the product, which is a delta H. But don't forget, there's also this one here between the intermediate and the product that is also a delta H. Right? We also have two different activation energies. We have the activation energy for the first step, and we have the activation energy, which is relatively small for the second step. So what we can say about this reaction and the forward direction thermodynamically is that the reaction from R to I, right, that first step, the delta H there is actually very positive, right? Here, let me move this so I can actually draw here. But essentially, that's telling us that the first step is not very favorable, which is not surprising because we end up with the missing octet right up here, right? And that should always be relatively unfavorable both thermodynamically and kinetically. Second step we have is the intermediate heading to the product, which in this case the delta H is negative, so that part is actually favorable. But overall, the reactant to the product, which is that third delta H we have there, is positive. So we would say that thermodynamically, the reaction is unfavorable, right? Because the overall reactant to product gives us a positive delta H. Kinetically, when we're looking at those activation energies, right, we see that activation energy 1, right? Sorry, we should probably label these. So for the first step is much greater than the activation energy of 2. And more importantly, when we're looking at things that have multiple peaks, the highest peak, right? If we take a look at both of them, EA1's peak, that transition state is higher than EA2. That highest peak is what we call the rate determining step. And this name is just because it's the slowest step, right? And so EA1 is slow, right? It's very slow. So looking at that term, rate determining step, all it's saying is that it is the step in the reaction that is the slowest and thus rate determining. Okay. And so whenever you see something with a very high activation energy peak, you can think of it as probably being the rate determining step. So if this is the forward reaction, what does the reverse reaction look like? So for the reverse reaction, we're actually going to start on the product side, right? We're going to have this guy with some H3O plus, which I'm actually going to fully draw out here, and some Br minus that'll come into play in just a second. So for this reaction, in the original forward reaction, what we saw was step two was that the H2O was taking a proton from the alkane, forming the alkene. For the reverse reaction, it should be the exact opposite of that. So it should be the alkene is taking a proton from the H3O plus to form H2O and the missing octet carbon. So if we were to draw that, right, the alkene has electrons, so it could pull from here. It's gonna give us that proton right there alongside some H2O. And then the first step of the reaction, step one up here for the forward, was the bromine breaking apart, right, dissociating from the complex there. And now what we're going to see is that if the reverse of that would have to be the bromine associates with that. So it's going to, whoops, it's just going to associate with that positive charge right there. And we end up with the alkyl bromide and H2O. So again, it's two steps, and each step is the exact opposite of the original direction because that is the principle of microscopic reversibility. If we were to draw an energy diagram for this, right, the energy values thermodynamically should be the exact opposite of what we saw up here, right? So in this case, we still have our high intermediate, but they're reversed in terms of whether or not the reactant or the product are the lowest energy value. So in this case, if we're drawing all of our peaks in between, you'll notice something interesting, right? So this time, if we look thermodynamically, right, we still have the three delta H values, and we even have a very large one from the intermediate to the product. But for our activation energies, notice something slightly interesting. It's still the first one that ends up being our highest value in our rate determining step, right? Which is a little odd because remember that technically this first hill right here is the second step from the one above, which was the faster step before. So looking at this thermodynamically, right, we'll talk about kinetics in just a second. So thermodynamically, very simply, the reactant to intermediate, that delta H is still positive, right? But then our intermediate to product, that delta H is still negative. But now our overall reactant to product, delta H, is negative. So the reverse reaction is favorable, right? Because remember in our forward reaction, the reactant to product is a positive delta H. That was the one that is the opposite sign between the two. Now then, kinetically, the first activation energy is much greater than the second, right? And so essentially what you see is that in the principle of microscopic reversibility, remember what I originally said was that thermodynamically everything swaps, but the kinetics can change drastically, right? Even though the reaction steps are happening in the reverse order, the activation energy for those reaction steps is a little different between the two. Okay? So let's move on and let's look at these transition states. Okay. So transition states look like the molecules reacting. Okay. And so essentially, what we're going to do here is we're going to treat these in a very similar way that we were treating resonance hybrids, right? Because they kind of act the same way. Essentially, we're going to set up a couple of rules that are important for drawing transition states because it's useful to know what these look like. So the first one is all bonds that are formed or broken in the step of the reaction are partial bonds, right? And then the other one is anywhere charges are present is partial charges, right? Notice how those two statements are the exact same as what we said for our resonance hybrids before, right? But the other thing with these transition states is they happen at the end of every step, right? So you should have one transition state for every step of a reaction. All right. So let's say we were focusing on back to this original forward reaction here. Let's say we were focused on that first step and we were looking at the transition state of it, right? Essentially, that step was taking our alkyl bromide, dissociating it, and you end up with the bromide and the missing octet on the carbon with the positive charge. Well, the transition state of this, which we do put in brackets alongside this little double dagger to say it's a transition state, would be the bromine and the carbon bond is broken. So that's going to be a partial bond between them, right? And at the end of the reaction, the bromine ends up with a negative charge and the carbon ends up with a positive charge. So that there would end up being our transition state. And one thing to keep in mind about these is that we would call them transient. All right. And the word transient just means exists for a moment, but it is non-observable. Right. And the reason it's not observable is if we're thinking about these energy diagrams here, this is the very top of the energy peak. Right. And right up there at the very top, essentially, is this spot where it's so high energy, it just wants to get to something that's lower energy, and no matter where it goes, it'll go somewhere lower. All right, so these exist only for a moment. They're not really observable. But there is a postulate that we actually need to keep in mind because it's very important for understanding how these transition states actually work. All right, and that is this guy named Hammond came up with this really good idea. It's Hammond's postulate. And what Hammond's postulate states is that the transition state structurally, oh man, I cannot spell, structurally looks like whatever it is closest to in energy. Okay. This adds an interesting piece to our transition states because it's essentially telling us what does the top of that peak actually look like, not just this little drawing of a transition state, which the drawing is still correct, but there's one other thing we need to keep in mind. So looking at this reaction once again, right, we've drawn it out multiple times, but one thing that you need to look at is if the transition state structurally looks like whatever it's closest to in energy, it's essentially saying is it going to look more like the products or more like the reactants? The products over here are completely dissociated, right? And so what that's telling us is if it looks like the products, it's really not going to look like there's much of a bond there, right? It's going to be pretty far apart. Versus our reactants, those are completely associated. So essentially what that means is if they are completely associated and the transition state looks like it, the bond is going to be very close. Okay? And so that gives us two different possible transition states. We have one that is like the reactants, and we have one that is like the products. So looking at the one that's like the reactants, it's like we say, it's going to look more like it's associated. All right, so our bond between our carbon and our bromine is going to be closer to association, aka it's going to be short, right? So when we look at our transition state for something that looks like the reactants and that bond is associated, it's going to be a little shorter. Keep in mind it's really dependent on what reaction we're talking about, right? In this case, it is going to be shorter because the reactants look associated. It could be the opposite if we were looking at the reverse reaction here. Whereas the products, right, we'll draw this one very exaggerated. Essentially, that bond is going to be incredibly long, right? Because it's closer to dissociation, so it's going to be a long partial bond. Okay? So, looking at this idea, Hammond's postulate is essentially telling us which one it's going to look more like. And so in our energy diagrams, right, for this step in particular, we're doing this here, right, where our transition state is here at the top, but we already discussed that going from the stable reactants to the unstable products is going uphill. But you'll notice that Hammond's postulate says the transition state structurally looks like whatever it's closest to in energy. And the closest thing to that transition state is the products. So it's closest to the product energy. Therefore, it looks like products. So what that means for us is that this one right down here that we had originally stated exists, this one that's like the products, for this reaction, this is the true transition state. So essentially, we can predict what the transition state's going to look like by following our rules up here, just all bonds that are formed or broken are partial bonds. Anywhere the charges are present are partial charges. But now we also have this idea of we know the bond length based on where in energy our transition state is closest to. Okay? So let's do this exact same thing, but think about step two, right? Because this was a two-step process. Remember, each transition state represents a different step. So step two of this, I will remind you of because it was drawn up top, is when the water comes in, grabs that proton, and then you form the alkene. Okay? So for this reaction, the second step, which we had already described, is exothermic, right? Where our reactant is of higher energy than our product. So for this one, our transition state, we would say looks more like our reactants. Okay, and this one's going to take a little bit more thinking as we draw it out. So the first thing that I always recommend when we're drawing these transition states is I say actually draw out the transition state, and we can label the bonds as long or short later. We don't have to immediately draw them as long or short because, sometimes it's a little easier to just draw stuff out first. So for this transition state, we got to think about what bonds are breaking and forming. And the first one that I see is that the carbon-hydrogen bond is breaking, right? So that's going to be a partial bond. The hydrogen is also forming a bond to oxygen, right? That's what that other arrow represents, is the oxygen forming a bond to the hydrogen, just like other acid-base reactions. The oxygen still has these bonds to these other two hydrogens right there. And then the last bond that we're forming is the alkene, right? Because we didn't draw that out just yet. So the other thing we need to do is we need to input our partial charges. So the carbon started out with a positive, right? So it should have a partial positive in our transition state. The oxygen ended up with a positive. So it should have a partial positive, right? Since there's no other charges anywhere, there's none other that we need to worry about. Now then, we have to identify whether or not bonds are long or short. Okay? And so how we're going to do that is we know that it looks like the reactants based on the um, statement we made just above. So the reactants have the bond between the carbon and the hydrogen. This one is fully associated, right? It has the bond between the oxygen and the hydrogen dissociated. And it also has the alkene bond dissociated. Right, and the reason I'm using these terms here is I'm just showing whether or not the bonds are there to begin with, or they're not there and they're being formed. All right, so what that tells us is if a bond is dissociated in the reactants, it's going to be long in our transition state, versus if it's associated, it's going to be short in our transition state. Whenever, keep in mind, it looks like the reactants. So in that case, that's telling us that our alkene bond is long, right, because it started out dissociated. Our oxygen-hydrogen bond is long because it started out dissociated, versus our carbon-hydrogen bond is short because it started out associated. All right. So an easy way to hopefully try and remember these is associated bonds, right? These are always going to look short. That is, keep in mind it's when you're talking about what the transition state looks like, versus dissociated bonds are the ones that are long. Because remember, the idea is going to be opposite if we were looking at the reverse reaction direction. Okay, so all this in mind, what you need to just know and think about is you need to kind of know what reaction energy diagrams look like, and you also need to be able to identify transition states and what they look like according to Hammond's postulate. Okay? But we're gonna change directions a little bit because we've been talking a little bit about kinetics, a little bit about the transition states. But what about delta H? Right? What about calculating enthalpy? Because a lot of what we've been doing is just making some of these assumptions of what the delta H should be based on what things look like. And sometimes that is true as what you have to do, but there is another way to actually calculate these that we have values for. So there's two types of bond cleavages, right? We have heterolytic bond cleavage, and we have homolytic bond cleavage. Sorry about that. Okay, for heterolytic bond cleavage, this is kind of what we've been looking at most of the time that we've been doing our reaction chemistry. Essentially, we have some bond between two atoms, A and B, where one of them ends up taking all of the electrons, and we end up with A having a positive charge and B having a negative charge. And so, with a lot of these heterolytic bond cleavages, normally we measure these by the stability of the products versus the reactants. So think about stuff like acid-base chemistry, right? Remember that we were using the stability of the base and conjugate base to decide whether or not something was going to be higher or lower enthalpy. But there is this idea of homolytic bond cleavage, which is where you have some A and B molecule where the bond splits evenly, right? And essentially what that means is that rather than two electrons going to one of the atoms, instead each atom takes one electron from that bond, right? So you can think of this as just a single electron, and these are a little bit easier to measure in terms of something called bond dissociation energy, right? So these are measurable by bond dissociation energy, also known as BDE. Okay? So, looking at this idea of bond dissociation energy, the first thing that we need to think about is this idea of what we call radicals, right? Because radicals are that single electron, right? So we can think about it as, let's say we had a hydrogen with a radical, and this is a single electron. So what you'll notice is the formal charge for hydrogen, it wants to have one, right? Because it is hydrogen, it's the very first element. It has no bonds, so -0. But for its electrons, right? Normally we'd put lone pairs in here as two, but there's a single electron right there, so it's one, which means the formal charge here is 0, right? But the thing is, if we look at hydrogen's 1s orbital, it does not have a full valence shell. All right. And since it doesn't have a full valence shell, essentially what that means is that this wants an electron, right? To make it look a little more clear, we can also look at something like a carbon with a radical. So notice that when we're looking at the formal charge here, it's 4 minus 3 bonds, one unpaired electron is 0. But this only has 7 electrons around it. So it is missing an octet. All right. Anytime something's missing an octet, it's still reactive, right? It still wants to have an octet more than it wants a neutral charge. And so what this means is we can actually make a blanket statement about radicals, and that is that radicals, right, which are these single electrons that are unpaired, radicals are electron deficient, right? Because they want to fill that octet, or they want to fill that valence shell in the case of hydrogen. All right. So radicals do have this interesting reactivity that we'll take a look at in the next lecture. But first, we need to talk a little bit about this idea of bond dissociation energy, also known as BDE. Okay, so bond association energies can be found in a BDE table. Right, I will be putting one of these up on Canvas so that you'll be able to see it. But essentially, there are BDEs for almost everything, and these will be available to you on your exam. But the idea of a BDE is the same thing that we were talking about up there, where you have two atoms that split apart equally and they give each other radicals. So if we were to look at an example of this, let's say we took H2 and it did a homolytic bond cleavage, right? So it's breaking apart that hydrogen-hydrogen bond. What you end up with is two hydrogen radicals, right? And if you look in a BDE table, what you'll find is that delta H, in this case, is 104 kcals per mole. Okay? And so essentially, this is a direct measure of enthalpy for this type of bond breakage. There are a lot of bonds in there, so another type that we could look at is, let's say that we were looking at two iodides, or sorry, just iodine in general. Let's say that this went through a homolytic bond cleavage. What we'd see is that you form two iodine radicals, and the delta H here is equal to 36 kcal per mole, right? And so notice that these BDEs can change drastically. All right. These are very different BDEs. But the question is what makes them change? Okay. And the answer to that is the same as everything that we've ever talked about, right? Bond association energy is affected by radical stability. So one thing that you might have noticed by now in chemistry is that stability is an incredibly important term. All right, because essentially it guides almost everything that we talk about. So BDE is affected by the stability of the resulting radical. And so to show this, the first thing that we actually need to do is we need to take a look at two different homolytic bond cleavages. Also, notice that this entire time when I've been drawing these electron flow arrows, I've been showing them as these single-headed arrow. So keep in mind that every time that we've been talking about um, electron flow, and we see this double arrowhead, right? So two, or I'll just call it a double-headed arrow. This is representing two electrons, and then a single-headed arrow is representing one electron, right? So that's why when we're looking at these, I'm showing one electron going to each atom there. So looking at two examples of a BDE, right? The first one would be something like methane splitting. So this is carbon and hydrogen radicals. The delta H for this is actually also equal to 104 kilocalories per mole. But interestingly, if you just change what is attached to that carbon to, instead of being hydrogens, they're all methyl groups, and you're still breaking this CH bond, what you'll see is that the BDE for this is very different. Even though we're still forming a carbon and a hydrogen radical, delta H here is 91 kilocalories per mole, right? And so the difference between these two is this is a 13 kilocalorie mole difference, which is pretty large, all things considered. So That tells us immediately that one of these radicals is more stable than the other. But the question is, how are radicals stabilized? And the answer there is there's two different ways. The first one is everyone's favorite friend coming back again, resonance. All right. So resonance stabilizes radicals the same way that it stabilizes charges. Okay, if we were to take a look at this bond association between this hydrogen and this carbon, it ends up forming a radical along with H dot. And for this, what we would see is that the delta H here is 87 kcals per mole, right? Which is even lower than the ones we saw up there. But the reason is because once it's in that form of the product, the radical can perform resonance. Okay? And so it can essentially go from one carbon, form the alkene, and move to the other one. And it's the same as any other time we've done resonance, where in this case, it shares the missing octet, which stabilizes it. Okay? And notice for this resonance, it's a little different from what we've drawn many times before. Because in this case, you have three different arrows shown. And essentially what it is the first one is the radicals donating one electron to form an alkene. And then the alkene is splitting apart to where it's using one electron to form the alkene, and the other one becomes the radical on the other side. So resonance can stabilize radicals, right? And it stabilizes them quite a bit. But the thing is, that doesn't account for the stabilization up here because these are all sp3 hybridized carbons, right? So the second type of radical stabilization is something called hyperconjugation. And hyperconjugation is the stabilization of a lack of electron density by slight orbital overlap to quote unquote, we're calling it fill the empty or partially empty orbital. Okay, so what does this even mean? Essentially, what we're going to find is that one statement is true. If you remember, um, carbocations, right? These plus charges, they immediately made something sp2 hybridized, right? This was very different to something like a negative charge, which was sp3 hybridized. And you'll remember last time we talked a lot about how it's because of the positive charge and where it sits in comparison to the nucleus. But the thing is, that's not the entire truth. The other part of the truth is this idea of hyperconjugation. But the other thing that you need to keep in mind is that radicals are also going to be sp2 hybridized. And it's all because of this idea of hyperconjugation. So what it is let's say you have a carbon that has a radical on it, right? That radical is going to be sitting in a p orbital, okay? Because it is sp2 hybridized. And so essentially, if we have a carbon connected to it that has something like a CH bond, right? And we'll draw the other two out as just normal bonds. But check it out. The two electrons in this carbon-hydrogen bond essentially are kind of aligned now with that carbon with the radical, right? Because keep in mind, since it's tetrahedral, it can rotate to a point that is kind of eclipsed with the p orbital of that radical. And so what this does is it creates this overlap, right? It has a slight donation via a weak overlap. Okay? And if we're giving some electron density to something that is electron poor, it's going to become more stable. And the thing is, the more CH bonds you can do this with, the better. But you can only do it for one bond connected to the carbon that's connected to your radical. So this is trigonal planar, right? So we have one thing going back into the page, one thing coming out. If those were also carbons with bonds like this to hydrogens, they could also perform this donation. But keep in mind, it's not like the electrons are actually flowing there. They're just helping, which is why I put it in quotations as filling that orbital, right? They're helping it feel more stabilized, but it's not necessarily the electrons are moving to that area, okay? And the one thing that you really need to know about hyperconjugation is that it occurs for CC or CH bonds adjacent to carbocations or radicals. Okay? So that's the one thing that you need to also keep in mind is that it applies to carbocations. So if we were looking at something like this carbon here that has an empty p orbital, we could draw the exact same drawing where this is giving some beneficial overlap to where that carbon has its positive charge. Okay? I'm not going to draw the other two parts. I'm just going to put them as R for now, but you get the point. So essentially what this means is that radicals can be stabilized by this, and so it now gives us another way to classify radical stability. So if we were looking at something like this chart down here, right, the least stable radical would be, for example, something that has no hyperconjugation, like the CH3 radical, right? It has no hyperconjugation. But something that's a little better would be if the carbon had a CH3 attached, right? Because now it has one source of stability, right? Because hyperconjugation from that CH3 is going to end up stabilizing that radical. Now, that being said, it's a little better if there are two CH3s attached, right? Because that is two sources, and it's even better if there are three CH3s attached, right? Because that is now three sources of stability. But none of these are better than if you were to have resonance, right? And the more resonance, the better. So essentially, the radical right here that only has one resonance form, right? Which was, of course, the one that we had already drawn. Right? This is relatively stable, but even better would be something like a radical source off of an aromatic ring where it has much more resonance, right? So the most resonance also gives us the most stable radical. So, with that being said, all of this is going to come into play as we look at next lecture, which is going to be talking about something called radical halogenation. But essentially, this lecture was a lot about energy, a lot about stability. It will show up on your exam, but it will not be as heavily emphasized as some of the stuff that comes around later. So I'll see you next time when we start to talk about radical halogenation. But until then, Just keep these things in mind. See you then.